So why make a video about motorized focusers? Well, I'm relatively new to astrophotography, and I'm trying to learn as much as possible about procedures and gear to find things that will really make a difference in my photos that I can actually afford. I definitely ran into the problem that it was hard to focus when the scope shakes because you're touching it with your hand. So as an impulse buy, I got one of these motorized focusers because people said it was better, and it is. But after installing one and digging into it all, there were a number of downstream effects that became apparent that I hadn't anticipated. So let's dive into, wait for it, the ins and outs of motorized focusing. Why use a motorized focuser? Well, there are few things in long exposure astrophotography that are absolutely essential to get right. Polar alignment and telescope focus are a couple of these. Well, it turns out that a focus motor greatly enhances focusing precision and repeatability, but also increases the number of complications around the task of getting good focus. So these are all the things that have come into the equation for me since installing one of these on my scope. First of all, you don't need one for visual observing unless you work with truly large telescopes at very high magnifications. For astrophotography, a motorized focuser allows precision control that's also repeatable. You can make finer adjustments than are possible with your hand, since just the act of touching the telescope to focus it shakes it enough that you can't tell if it's better until it settles down. With one of these on your scope, you can then employ automatic and computer-aided focusing, which allows you to focus the telescope remotely, even over the internet for a remote telescope setup. What exactly is a motorized focuser? Well, in most cases, what we're really talking about is a focus control motor added onto your scope's regular focuser with a bracket and screws that allows the motor to attach to the focusing control shaft. You typically remove the fine-tune existing focus control knob on your scope and then use the bracket and screws to position the motor in a place where a coupler can attach to the focusing shaft and the motor shaft. If you want, you can go get a complete new focuser with a built-in motor, but this is expensive and maybe not your first step unless you were thinking of replacing your focuser anyway. The installation of a motor on your focuser is technically not permanent, but it's close. Once it's on there, it's on there. There are a number of hard-to-get-to screws to tighten, and you definitely don't want to be fooling around with that in the field. So if you think you're going to buy one of these and move it from scope to scope, I think you'll find that it's more trouble than it's worth. I did, so I have one on each photographic scope now. With the majority of setups, you lose the ability to focus manually, which makes focusing initially take longer, but it's better. So it's the classic trade-off of convenience versus precision. Some third-party focusers, like the ones from Moonlight, offer a slip clutch design, which still allow you to turn the knob by hand. But now you're in for a new focuser and motor, and that's probably going to be $700 to $1,000. Remember, these things are powered, so make sure you've got a plan for a power cable and a USB cable to control it. This is funny. The first time I used my newly installed focus motor on an actual imaging session, at the end of the night, I power down, pull the scope off the mount, go to put it in the case, and realize that the focuser draw tube is still most of the way out. Now, normally you just grab the focuser knob, rack it back in, and stow it, but no! I had to get out the computer, the power supply, the USB and power cables, just to return the draw tube to its fully retracted position so I could stash the scope. Only made that mistake once, well, twice. Motorized focusers give an absolute position in the form of a numeric readout. Quite often, 0 to 65,535, which makes certain kinds of precision focusing activities possible, like software-controlled automatic focus routines. You can establish focus settings with precision for various filters you might have, a filter offset. You can find approximate focus quickly by recording and recalling the numbers. It allows you to dynamically change focus over a long imaging session as the temperature changes throughout the night. The motor also has an ambient temperature sensor so that absolute focus values can be referenced against ambient temperatures. And you can return the telescope to the same focus point as the night before, so you can take your flat and calibration frames the following day. Camera rotation is also important here too, by the way. Some models are telescope series manufacturer specific, and others are more generic, using the mounting bracket and screws method. If you have a mainstream Celestron or Meade product made relatively recently, there's quite a number of scope-specific focus motors out there. Pegasus Astro, Moonlight, and ZWO make motors that can be adapted to most any scope with a little ingenuity on your part. You may want to consider the amount of weight the motor will have to hold. The camera plus the filter wheel plus the reducer, it all adds up. The focus motor needs to be able to have these things hanging straight down if your scope is pointed at the zenith, and still be able to hold it absolutely motionless and move with precision, no slippage. Allow some headroom here. Don't cut it too close on the weight limit. Most of these things are pretty strong though. Okay, so how much is this going to cost? On the low end of things, you can get a motor and brackets for just under $200. A little more if you want a temperature sensor and a hand controller. These are controllable by computer via the ASCOM protocol. There are a range of products up there up to about $600. At around $700, you start getting to the realm of complete focuser replacements, which can get up to about $1,500 depending on your required diameter and load capacity. At this level, you might want to look into a combined focuser camera rotator, since if you're looking to automate your scope, you might as well automate everything you can for enhanced repeatability. A camera rotator combined with computer-based plate solving allows you to repeatedly get your scope exactly on target and camera-oriented just like last time to complete an image series longer than what you can shoot in one night. This is also important for large targets or multi-panel mosaics. These all-in-one solutions like the Moonlight Nightcrawler, which by all accounts is a great product, come in at around $2,400, but you can get a motorized camera rotator for only $700 from Pegasus Astro, which, when combined with a standard focus motor, could get you into all of this for about $1,000. In order to reap the benefits of usable, repeatable results, at the beginning of the night, you should make sure the focuser is racked all the way in, and you tell the software to define that as 0. You should do this every time if you want your numbers to be consistent, unless your focus travel is longer than the number of steps your focus motor actually has. My Celestron Rasa is like that. The 65,535 steps in the focus motor are not enough to move the mirror its entire travel length. So I had to set an arbitrary 0 point somewhere so I could get a good focus number that didn't get me all jammed up at one end. One of the best reasons to put up with all of the extra complications of a focus motor is having the ability to do focusing that's not simply subjective, but arrived at through a series of tests to make sure that the focus is as good as it can be with the seeing you have at that moment. The basic concept goes like this. Get your telescope roughly in focus using a batten-off mask or with your eyes. Take a short test photo through some kind of neutral filter, like a luminance or light pollution filter. Have the software analyze it and report a focusing score. Try different focus values to find your best score and use that focus point for your shots. There are automated and near-automated focus routines in many of the popular image capture software programs, but the two I'm most familiar with are Sequence Generator Pro and SharpCap Pro. So my remarks here are going to be based on what you see in those apps. So how does the computer tell what's in focus? Well, the two most common ways you see used are the HFR value, which stands for the half flux radius, or the FWHM, full width half maximum method. There's some distinction between these two, but that's above my pay grade. But when graphed out, they look about the same. The more in focus something is, the more sharp this peak will be in the graph. You will probably recognize this from the guide star focusing area of PhD 2 guiding. In any case, you want the HFR values to be as low as possible, and you can get them with the narrowest peak on the graph. While PhD 2 uses HFR to calculate the sharpness of your single guide star, you can also plot HFR values for a whole bunch of stars in an image and then average them to obtain your focus score for that image. If you can, it's a good idea to tell your software not to include the stars near the edge of your image, since they would most likely be the ones subject to optical distortion, and therefore not an accurate indicator of focus. An automated focus routine generally goes like this. First, you want to set some initial parameters, since there are a number of variables in the automated process. The number of steps. This should always be an odd number, so you can have a center value that's supposedly in focus, surrounded by an equal number of out-of-focus values. For example, with 9 steps, there are 4 out-of-focus exposures on either side of your supposed best one. After you really understand the focusing characteristics of your rig, you might be able to cut this back to 7 or even 5 samples so it doesn't take so long, but 9 is a good place to start until you've made this work well a number of times. Choosing a good step size is key to success here. The step size is the focus number distance between each of the focus point samples. Every focuser will require a different step size, but the general thing to remember is that the individual steps are really freaking small. On my rigs, a focus change of 25 is smaller than the smallest turn of the knob you can make with your finger. That's how fine the focus motor adjustments are. So in setting your step size for automated focusing, the steps need to be far enough apart to make a meaningful difference in focus, but not so far apart that you end up way off in no man's land and you can't get a consistent, accurate final HFR focus value. For instance, if your first focus point is so far out you can't even see stars anymore in your first focus shot, your step size is too large. The stars should be pretty out of focus, but still recognizable as stars. There are some formulas for step size out there, but I found them to be complicated and hard to understand, so try a step size of 85 to 150 and see what happens. Focuser backlash. When you start an automated focusing run, the first move is to rack the focuser out and then come back in gradually for the rest of the run. If you have some backlash in your focuser, the step size between focus point number 1 and 2 will be off, and your second focus point will end up being too high because it was the backlash that was getting taken out during the move from 1 to 2 instead of being an honest step of 125 or whatever. So try and manually get the backlash out before you start the run by going out farther than you need to, which would be somewhat larger than 4 times your step size. If you see a backlash compensation feature in your autofocus software, you should probably turn it on. So let's get focused. Find your best eyeball focus with a Bahtinov mask and write down the focus number position the motor reports to you as a ballpark value. Get the ASCOM driver screen for your focus motor up on your computer so you can see the actual numbers read out as the autofocus procedure unfolds. Enable your autofocus routine in your software, and it will first rack the focuser out to a specified amount, take a quick exposure and analyze the HFR of the photo, and plot it on a graph of focus position versus HFR value. It will then rack the focus in a little according to your predetermined step size, and take another photo and get the HFR value and plot it. If things are going well, it will be lower than the previous sample. If not, don't worry, it might just be the backlash in your focuser. For the third sample, it will rack it in again, and this time the plot on the chart should definitely be the lowest so far. The fourth exposure will be taken after another focusing adjustment, and it should be lower still on the graph. Assuming you chose 9 sample steps for your full focusing run, this next one, number 5, should be with your focuser at the same position you had it at after focusing with the mask, and the plot should be even lower still on the graph. For focusing exposure number 6, the focuser is now racked in slightly farther than your mask-obtained focus value, and therefore should be slightly out of focus now, and the plot on the graph will probably be higher. This will continue for exposures 7, 8, and 9, each one getting more and more out of focus and higher on the graph. At this point, your software will look at all of these focus values and calculate a curve that looks like a V or a U that will generate a best focus number, which should be relatively near your starting number, but perhaps 20 to 50 focuser numbers on one side or the other, depending on how accurate your initial mask focus was. Sequence Generator also gives you a confidence number, listed as a percentage as things are going along. As you get past focus sample point number 5 and are proceeding to number 6, keep an eye on the confidence number. And if you see 100%, you should definitely write that number down somewhere in case you need a second opinion later. Once the autofocus run is complete, the software will usually ask you if you want to move the focuser to that number, say yes, and then it will take a verification exposure and analyze the HFR of that to see if it's a better value than all the ones obtained during the run. If all goes well, this is your focus number for that camera at that temperature with that filter for the night. Write this value down in place of the previous one. This is a pretty good value to use as a starting point from now on. If things don't go well and you end up with a confusing, zigzaggy graph and a confidence numbers in the low 20s, you are probably dealing with some combination of too small a step size and backlash in your focuser mechanism. Try tripling the step size value and running it again to see if you get it closer to the V or U-shaped curve. Now there's other types of focusing too. HFR is great, but it only works on stars. So SharpCap has a few other tricks up its sleeve to help you get focused on non-point sourced objects like planets and the surface of the moon. It uses a method called contrast detection for edges of things or brightness differences between object and background sky. For things like the surface of the moon, you can employ the Fourier edge detection method. Both of these methods display a bar graph for the focus score. The more green bars you see, the better. Keep notes. This is very important. As you start using your motorized focuser, keep notes in your phone or computer. A spreadsheet would be ideal, but just jot it down somewhere like Notepad or Evernote. Keep track of the following: which rig you're using, if you have more than one, the focus number, the filter being used, and the ambient temperature. This will help you greatly in trying to determine whether temperature changes are something you need to be concerned with and whether or not all your filters are in focus at the same number or not. Likely they won't be, but after enough experimentation, you'll be able to determine things like the astronomic sky glow filter is in focus 53 steps farther out than the RGB set. This will allow you to establish a filter offset, so even if you start the night in focus at a slightly unusual focus point number, you still know that when you switch to the astronomic, it has to rack out 53 additional steps, and then your shooting software can restore it to normal when you shoot the RGB frames. This kind of thing is just impossible to do by hand. Most of these units come with some kind of temperature sensor, either built in or a detachable cable or something like that. And the software that controls the focuser is also reading this temperature data and including it in the header of the FITS file of every image you take. But why is it even on there, you might be asking? Well, when I got into this, I was flabbergasted to find out, although it does make sense, that over the course of a full night's imaging, the temperature can change enough that your telescope, the optics in it, and everything can physically contract enough to cause an actual change in focus. Not much, but enough to take perfect focus and smear it up a little bit. This is one of the main reasons why you see the carbon fiber refractor telescopes these days. Very little thermal expansion or contraction. Now, normally you wouldn't be concerned about thermal expansion or contraction. As a visual observer, you're constantly refocusing as you change eyepieces and go from object to object. In astrophotography, you stare at the same object all night sometimes. So depending on your setup, things can change and the temperature sensor is there to help. This is definitely a next level kind of thing. So once you've got your setup working and under control, you might want to start paying attention to the temperature focus number relationship and see if any patterns emerge. So you've decided on a product and you've installed it on your scope. Cool. The software is installed, it's communicating with the unit. What now? Well, you know those nights that are almost clear? Not really cloudy, but not really clear enough to actually do imaging? Well, that would be a perfect night to do some motorized focuser testing. You could do things like discover the best settings for the automated focus routine in your software. Step size is important, as mentioned before. Make a place to keep notes about focusing, because if you don't, it's going to get confusing, and you'll end up wasting precious imaging time under the stars chasing your tail on focusing because you don't have a solid baseline data from which to start from. Find the best focus number for no filter at all. Run 3 complete autofocus routines and average the final score numbers. Doing it 3 times back-to-back will give you some idea as well how much variance is present and acceptable in your telescope rig. Find the best number for all of your different filters using 3 complete passes of autofocus. See and record what the offsets are referenced to a particular setup, like no filter if you have an open spot in your filter wheel, or perhaps you have a sky glow or luminous filter that you'd call your no filter standard. And then eventually you can see if dropping temperatures over the night affects your focus enough to require adjustment. Lastly, remember, having your photos be in focus is something you just can't fake. It's got to be right, or you really aren't getting the result that you want with respect to how much effort it takes in the first place. There's few things as demoralizing as realizing an entire night shooting is not really usable because you blew it somehow on focus. It's really been an amazing learning experience diving into this whole autofocusing thing. And it's so great that the technologies around these days let us have the same capabilities professionals use for a couple of $100. This is Bill the Sky Guy saying, Carpe Noctem from Hilton Head, South Carolina.